All right. One more day, one more coordinate system. Last time we got together, we talked polar coordinates, radial direction, a theta direction perpendicular to that. Today we're going to talk about one more new coordinate system that can be useful for solving these problems. Then I'll try to draw some comparisons between what we did today for normal tangential to what we did last time for polar, so you can see maybe I can use this one, maybe I can use that one, maybe we could use both. Try to figure out which one is a little better to use for what problems. So that's our goal for today. So new coordinate system, we want to describe velocities and accelerations in this new coordinate system. This kind of matches a little bit of what we did the first day of class. We've got some path. Any point along this path, we can draw a tangent. That's kind of tangent. Our velocity, we talked about the first day, at any point is going purely in that tangential direction. Well, we also said that perpendicular to our tangential direction, we've got a normal direction. We really talked a lot about this already. So we said velocity was purely in the tangential direction. We talked about acceleration having a pair of components, a magnitude change, whether we're speeding up or slowing down. So that part of the acceleration might be in the tangential direction if it's speeding up, the other way if it's slowing down. And then it's got a normal component, and that's from the direction change. So we talked about like sitting in your car, slamming on the gas, accelerating forward, hitting the brakes, decelerating, and then making turns. And then turns, you feel that acceleration as you're cruising around the turn, and that's what we get in the normal direction. That change in direction while moving at some velocity is going to give us acceleration in that normal direction. First thing, how can we go about defining the tangential direction? This is kind of maybe an intuitive way to do it. So if we have some curved path, and we have our position vector at multiple points. So I've got a position vector at, say, time 1. Position vector again at time 2. Our delta r is just the distance between these. So if we subtracted them off, it would look something like this. R2 minus R1. The path we're actually moving on, maybe now I'm going back to my left, the path is this arc. This would be my change delta S. So the change along the path. How far have we actually moved along this path? So what we're going to do is we say, hey, as our tangential direction is the limit as delta S goes to 0, delta R over delta S. The idea being here, hey, as this change gets squeezed down in smaller over smaller and smaller and smaller arcs, this straight line is essentially going to approximate this arc. So they're going to have magnitude 1 when I divide them out. But this direction for the vector part is going to be pointing along the tangent to where we want to go. So, not terribly useful or fancy. Just remember the tangent direction is going to lay on that curve and point in the direction we're going. All right, we got the tangent direction. Let's define the normal direction. So for the normal direction, we're going to talk a little bit about curvature and bring in some other things before we really define that normal. So let me draw some more squiggles. All right. Purposely drew some big sweeping arcs and then some little tiny ones. So what we have is this function, or the definition of kappa here. This is our curvature. And what's that looking at? That's defined as our change in our tangential unit vector over path. So how much is that unit vector changing over the path? So if we kind of think about what's going on here, if my pen is riding this path, and it's trying to maybe go at like a constant velocity. So here it makes kind of a fast turn. Here it's going a little slow, making a little turn. And then when it gets here, it's got to switch directions really fast. Right? So kind of medium speed turning, changing. Here nice and slow. Here super fast. So where I've got a big old smooth sloping curve, our tangent direction changes very slowly. So this, if I picked a point over here, I could draw a circle on this. And imagine I was good at drawing circles. I'd have a circle that fit into that shape. Yes, just like that. I hit the side. Okay, so I'd have a circle that fit this shape. This circle has a radius, rho. We call this the radius of curvature. Our radius of curvature is the inverse of curvature. So we just threw two names at you just to confuse you. But the idea being, hey, where the radius of curvature is large, our curvature is small. So as I can fit a big smooth circle in here, I have very low curvature. But if I go to this point where it's really tight, and I try to draw a circle for that one, I was a little more successful. But this would have, this would be a tiny radius of curvature, so it would have a big curvature. It's really curvy, and it has a tiny radius of curvature. They're just inverses. We'll use them in our definition as we go. This idea of being able to fit a circle anywhere along a curved path, like over here, I'm giving myself a pretty good start as to what the circle might look like. This circle, you can imagine, as you try to draw it at all these different points, it's going to change its center location. It's going to change its radius. And heck, it might even flip-flop sides of this curve. And in certain points, maybe right here, the line is just about straight. So if this line was perfectly straight, the radius of curvature would go to infinity. It would be like a straight line, so the radius would have to be a zillion meters long. So in this case, when we're defining tangential direction, pretty easy. Point along the curve in the way we're going. So I drew an arrow over here. We're moving left to right. The normal direction, always towards the center of curvature of this imaginary circle that we can place at any time. So that's how we're going to find our normal. Coordinate system, we need 3 vectors. So we have a tangential, A normal, if we do t cross n, that's pointing up. That's going to be our z, or our k hat direction. So if I look at it for this first circle I drew, t cross n, point my fingers towards t, cross them towards n, my z direction is down, pointing into the page. As we fly around this curve a little further, I get to no man's land, right here, where I have a tangential direction, but if I'm going in a perfectly straight line, I've got no normal direction. Could be over here, could be over there. It's a straight line, so I don't define a normal, and I don't define the binormal. But then once I get over to my big, smooth, perfectly drawn circle, I've got, again, my tangential direction. But now my normal points towards the center of curvature, which we'll pretend is right there. And if I do t cross n, now my z direction is pointing up. So this guy's a bit of a moving target for us, where the tangential, the normal, tangential is pretty easy. We just kind of like follow it with our finger. But the normal can be pointing in, and then it can disappear. And then when it pops back in, it can be on the other side. Normal, 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 disappear, and pops back in over here. So how we define that third direction in a normal tangential system, we got to keep an eye on what the shape of our curve is at that point. That shouldn't give us too much trouble this semester. It won't really jump into what we're doing. So our normal direction, though, u hat n, is defined as 1 over the curvature times the change in the tangential direction over the path. All right. What is all this? The change in the tangential direction over the path. That was me taking this pen and going and saying, like, hey, look at how slow we're going here and how smooth it is. But then over here, it can be a big change because we're going on a tight, tiny little curve. So this guy has some magnitude. Its magnitude is the curvature. So we pop in the curvature just to normalize this to be a value of 1. So if we kind of take away the magnitude part, really what the story we're telling is that the change in my tangential direction over the path is the normal direction. So the change in my tangential direction over the path, we can think is perpendicular to my path, which is why we got these guys at right angles. So we talked a little bit about that on day 1, the fact that our normal direction is perpendicular to our path. All right. Osculating circle, we already talked about this. This was me drawing a bunch of different circles. So at any point along this path, I could draw a circle, radius equal to the radius of curvature for the given point, and that circle lays in a plane. That plane is our oscillating plane. Again, not that important for us. But understanding that t and n form a flat 2D plane, that third direction, t cross n, that's our binormal. So we've called that u hat of b for the binormal, or the third direction that we're trying to chase. The part I think that we need to really remember, just our definition of curvature and radius of curvature. So when I think curvature, I think, how curvy is that line? Well, it's pretty smooth here, very large radius, very small curvature here. It's very curvy here. Very curvy means big curvature, small radius. Just inverses, okay? So what is that radius of curvature? I was told we learned this in calculus, but I don't remember it. So here we've got a function. It looks like this. If we know what this function is, and in this case we do, y as a function of x is equal to 1 minus x sine x. So if I have a definition for what this path looks like, we can compute the radius of curvature at any given position x. Any one we want. And this is our radius of curvature equation. So our radius of curvature, a little bizarre looking, 1 plus the change in y as a function of x squared to the 3/2 power divided by the magnitude of the second derivative of y as a function of x. Obviously. Nobody remembers this, but we can use it to figure out curvature along this path. Also, a side note, those of you seeing equations like this, accelerations for polar coordinates, and getting kind of nervous about what the heck you're going to have to use for the exams would give you an equation sheet with all these things on them. You just like tear off the back of the exam and lay down, and then you can follow along. So don't feel like you have to memorize this, but understand how to use it. So the equation sheet, if you are interested, is on the course website. So under the week 0 module, there'll be an equation sheet. But for us, this will give us the curvature at any point x. But we need a function y as a function of x. Not always going to have that, but in this case, for this little problem, we do have that. So for us, we want to find the curvature at the local minimum. The local minimum right here. So what are we trying to do? We're going to draw a circle that sits in that. And we want to figure out how big its radius is. The radius at the local minimum. So I guess first thing, how do I find a position of a local minimum? Take yourself on that trip back to calculus. Think, to find a minimum or maximum, I take the derivative of a function and look at where that's 0. So what is that saying? It's like, hey, I want to figure out where the slope of this function is 0. And those are going to be mins or maxes. Right? So all the derivative does is give us the slope. If I want to find out where the peak or the valley is, where slope 0, that's what's happening. It's not changing. So for the min, I want dy dx, I want to set this equal to 0. So I take my equation. Oh, got to use the product rule. The derivative of 1 minus x is minus 1 times the second piece, sine x, plus the derivative of the second piece times the first. So 1 minus x. Derivative of sine x is cosine x. All right. This still isn't super easy to solve. Right? Like analytically, how do I figure out an x for all of this? I think the best way to do that is plug that in your graphing calculator. Plot the new function of dy dx. I don't know. Pretend like that actually is what the function would look like. And if you did that, you're trying to do root finding, right? Like, hey, where does this equal 0? Not that it all matches now with my real drawing. But that's how we could solve this. I could plot this function in my graphing calculator, look for the 0 crossings. This first one, max. The second one would be our min. This third one, which I have poorly drawn, would maybe be the absolute max for this problem. So if I thought a little bit more about what the curvature was, this might actually be right. But in this case, we're going to pick off the second one. We're going to say that x is equal to 2.24. That's our max value. And if you ran back to that figure that we showed to start and you tried to pick it off, it's about right. So we've got our x value that we're looking to find our rho at. So we want rho at x is equal to 2.24. Well, in order to get this, we need to look at our derivative at that point. Yeah, that's kind of good, because I just found the derivative. And at that point, it was 0. So life there isn't so bad. But I also need to take the second derivative and find the second derivative at this point. So if I start writing what I know, I've got the 1 plus dy dx at x is equal to 2.24. That's actually 0, so that makes our life easy. Square that to the 3/2 divided by the magnitude of the second derivative. Now I got to do work. The second derivative. The derivative of minus sine of x minus cosine of x plus product rule, because I got a 1 minus x and a cosine x. Got minus 1 cos x plus derivative of the second piece times the first. 1 minus x, derivative of cosine is minus sine. You can buddy these two guys together. There's two negative cosines. But really all we're going to do here is plug in x is equal to 2.24. To there, to here, to there, there. And then since we want magnitude, we're going to take the absolute value. I've got a lot of things written on my paper, but I think the answer is 0.45 meters, assuming that this function was given to us in meters. So what have we done here? If we can define a function, x as a function of y, we can figure out how curvy it is at any point. How do we do that? With this bizarro curvature equation, which involves us taking a derivative and a second derivative. Remember this first part? This first derivative is only equal to 0 because I was looking at a maximum. If I scooted over a little ways and I wanted the curvature over here, hey, I would just plug in my new x value into this and see what I got for our slope. All right, all that work, learning how to do curvature, so like we can finally talk about how that curvature relates to acceleration in tangential coordinate system. So that's what we were doing there the whole time. So if we start with velocity first, velocity in the tangential coordinate system, our velocity is easy to define. It's just, hey, our velocity, and it's the direction that we're going. That's a t. In the tangential direction. All of our velocity is happening in the tangential direction. So remember for polar coordinates, well, how much of that velocity was happening in the r direction, how much of that velocity was happening in the theta direction kind of depended on what the path you were traveling, and where you originally planted your coordinate systems to measure from. So tangential, hey, all my velocity is always happening in the tangential direction. Life is good. The acceleration, a little sneakier. So what's my acceleration? Acceleration is dv dt. So let's take some derivatives. Derivative of the first piece, v dot u hat t, plus derivative of the second piece times the first. V times u dot hat. Hey, we did this last time, trying to figure out what the derivatives of unit vectors are. So on the screen here, this uses a slightly different piece of math to get us to the same answer. So on the screen there, use chain rule to introduce a position variable, and then works back to our definition for curvature and radius of curvature to give us the answer. This, I think, ties in a little better with what we've done before, though. So let's do it this way. The time derivative of our tangential direction. We said that that was the angular velocity crossed with the original direction. Okay? So if our angular velocity is equal to omega in that third direction, our out of plane, we can start working through this cross product. So if I draw this again, u hat t, u hat n, and our k direction, this is equal to omega k cross u hat t. So if I start out in the k direction, pointing up, I put my fingers there, I cross towards t. That points me in the n direction. So I'm left with omega in the u hat n direction. Hey, this is almost useful. I've got n, for I've got my other direction now, but I got this omega, which is maybe a little bothersome. So that rate of change of our coordinate system. So if we think of at any point in time fitting a circle to this, and this one circle only kind of works for this point in time, but this omega corresponds to the rate these things are rotating at that point in time. So let us take a little trip down memory lane and see how this relates to polar coordinates. So for polar, if we had a circle here, our polar velocity, r dot in the r direction plus r theta dot in the theta direction. So maybe right away we'll say theta dot, that's our angular velocity. Let's change that to omega. Same variable, different name. All right. So if I'm going to look at a little circle that I drew, just for this split second in time, I'm not going to worry about r dot, because I'm going to look at a circle like it's as if it's traveling the circular path and the radius isn't changing. So just for now, that guy's going to stay still. So my velocity at this time is going to be r times omega, the radius of this circle, times the rate at which it's rotating, omega. Yeah. So that's what my velocity would be at the top. This can be rearranged to get our omega. Our radius of this circle at any given point in time, that's what we call the radius of curvature, right? So let's put that into a better form. We'll call that guy rho. Because at any given time, we can draw these circles, and we know the rho gets bigger and smaller depending on how curvy the path is. So here, the way we can kind of work this through, I've got omega is equal to v over rho. That's what I'm going to sneak in here. So the time derivative of my tangential direction is v over rho times my normal direction. And then my acceleration, we can rewrite v dot in the tangential direction plus, I've got one v and another v. Those guys become v squared over rho u hat n. Here's our acceleration that we need to fall back on to be able to use. So, tangential direction, v dot. How much am I changing my speed? Speeding up, slowing down. When you think of this as speed up, slow down. Maybe it's 0. Maybe I'm driving at a constant 52 miles an hour. This normal direction, v squared over rho. So the acceleration we're feeling as we're barreling around that corner at 25 miles an hour, v squared, over rho, whatever, 60 meters, or just mix up some funny units there, but some radius. You can see that acceleration, pretty heavy function of velocity. So if you come into a corner going 2 miles an hour, you might feel an acceleration. If you came in going 4 miles an hour, you would feel that difference squared, right? Because here, 2 times squared. So we go going 4 times the acceleration in that tangential direction. So when you're driving your car on the highway and you're making a turn, slowing down a little, you actually get quite a big benefit because it's a squared function on your acceleration. So keep that in mind when you're cruising around on the ice. But the radius, obviously, also a big factor here. All right, let's compare to last time. This is like any path. We've picked our point O. I want to look at polar and I want to look at NT for these two systems. So maybe the point I care about right here. Okay? So for a radial direction, I go from the initial locked point O through to the point I'm looking at, u hat r, positive theta counterclockwise, here's my coordinate system. For an NT system, hey, I said I'm driving up this hill now. So I got to find tangent to this path. And then my normal direction is perpendicular, so I got 2 choices, but it's got to point towards the center of curvature. So that tells me it goes this way. That's perpendicular. So if you've got some random curvy path, you can see in general there's no link between these two coordinate systems. What is your polar one points with reference to O, your NT just cares about the path. So there's really no easy way to jump between the two sets. But if I have a circular path, now we can do something. All right. And again, we're going to keep going up the hill here. So for a circular path, keep my colors working the same. The point I care about, my radial direction from my center point to the point. Theta is perpendicular. Hey, theta also happens to be tangent to this curve. If it's a circle, the tangent is perpendicular to the radial line. Well, if I'm going up the hill, my theta direction also is my tangential direction. But my normal direction, perpendicular to this, pointing towards the center of curvature, so back towards where we came from. So now you've got a go-between for these various coordinate systems if you happen to be traveling in a circular path. You can relate your normal and your radial directions and your theta and your tangential directions kind of by eyeball, depending on which way we're going. So I've got polar, and I've got NT. So for NT, the ones we just did, V dot U hat T plus V squared over rho in the normal direction. And then for polar coordinates, when we got together last time, R double dot minus R theta dot squared in the R direction, plus R theta double dot plus 2, there's a 2 in here, 2, R dot theta dot, and this is in the theta direction. If this was a circular path, we can get rid of some terms. So for a circular path, our radius is constant, so R dot and R double dot go to 0 because we're traveling an arc. So we can get rid of this term and get rid of that term. So if you look at what you got here, my radial direction and my normal direction are buddies, but opposite. So this term and this term can be related. Our radius, R, is equal to rho, because our radius of curvature is equal to the radius of our circle. And theta dot, remember that's omega. And did we just use that one page ago? Where we said for a circle, I did that somewhere, omega was equal to V over rho. And then in the tangential direction, what's our acceleration look like in the tangential direction? If we're not changing our radius, our speed change, or velocity change, theta dot, is equal to R times theta double dot, or this is alpha, the angular acceleration. So we've got an angular acceleration here. This is theta, angular velocity omega, and alpha. Alpha times R, that is my acceleration in the tangential direction, V dot. So these guys are buddies, and these guys are buddies. Oh, I drove past it. So it all kind of is the same for a circular path. And you say, well, I got two different ways to do it. Which one do I use? Do I use polar or do I use NT? If it's a circle, and I could use either, but I read the problem and I ask myself, what does the problem give me? If the problem gives me velocities, I use NT. If the problem gives me angular velocities, theta dot, or theta double dot. Then polar is typically easier to use, so I don't have to convert back and forth from an angular velocity to a velocity, or an angular acceleration to a linear acceleration. So just depending on what information I'm fed, one can be easier than the other to use. I was cruising Piazza the other day, and someone asked me, why is our angular velocity in the k direction? So I wrote some answer that involved a cell phone, and we'll see if it makes sense if I explain it real quickly, because all our velocities are going to be the same, right? So you got your phone out like this, and we think of the plane that this thing is sitting in as a 2D plane. So I can translate in x, I can translate in y. Hey, this could be r, and this could be theta, or n and t, whatever. It's just translating in that plane. But for this thing to move and rotate in that plane, I've got to spin that about an axis that comes up. So my z direction, if this was x, this was y, my z direction would point up. And for us to rotate about z, we're spinning. And again, this is planar, so everything has to stay in this 2D plane. In order for us to move on to the next dynamics course where you do 3D stuff and you come out of the plane, you would have to add a third dimension. Whoop, coming up and down, right? That's our z. But you would also need to specify z if I was going to rotate about the x-axis. So the x-axis goes horizontally here. So in order to rotate about that x-axis, I need to pick this thing up and flip it. Right? I'm spinning about the x-axis. A rotation about the y-axis, the vertical line of this phone, again, I need to come out of the plane to rotate this thing across. So for planar motion, you can pick your xy, your r theta, your nt, but we're always going to be rotating about that z direction. We just talked about nt that could flip, so it kind of look the other way, but that's just kind of a minor detail. Just keep in mind that this is not a rotation in x or y. Rotation in x would look like this. Rotation in y, it's my y-axis, would look like this. All requiring out-of-plane motion. So for in-plane motion, we can translate and we can rotate in z. Nothing else. All right? Let's look at one. Okay, we got a water jet shooting from this nozzle. We're given an initial speed, v0, 12 meters per second, and we're given an angle. We're coming out at 33 degrees. We want to determine the rate of change of speed of the water particles. So the rate of change of speed, my v, my velocity is my speed, the rate of change of that, v dot, as soon as the particles are ejected, as well as the corresponding radius of curvature. Radius of curvature is rho. So we want to find v dot and rho the moment they're shot out of this. So rho would kind of look like this. So we're given our angle is 33 degrees. And our initial velocity is 12 meters per second. Okay. Everything we've talked about today has been normal tangential acceleration. So our acceleration is v dot in the tangential direction plus v squared over rho in the normal direction. So imagine this is my water. It shoots out like this, and then it splashes down over here. Okay. How do I put all this together? There's one thing that we got to think 2 classes back to think about. If this water particle is a particle, and we're shooting, this is just projectile motion with gravity in the downward direction. So I've got my acceleration is given as minus g in the j direction. I know what my acceleration is because projectile motion. But I've got acceleration. If I want v dot and v squared over rho, if I want rho, I need to get this acceleration not in terms of y, but in terms of n and t. So I've got u hat t u hat n. This is supposed to be at this point of launch. And then gravity coming straight down. And we know our angle is 33 degrees. So if that angle is 33, this angle also 33. I just go like this. Boop, and I rotate them both the same angle, right? My simple brain works this way. If that one's 33, this one's also 33. So what I want to do is I want to break gravity up into these various components. So how much of it is acting in the tangential direction? That's this piece. How much is it acting in the normal direction? That's this piece. This much. Okay? So we can write that out. A sub t, the tangential, is going in the negative direction. So minus. The magnitude is g. And this here is also this one. That's my sine leg. The normal direction. G now points in the direction of the normal, so that's positive. Magnitude g. And that's my cosine leg of this little triangle. So really what I've done here is I've just taken my acceleration in x and y, and I've converted it to my nt system. We got minus g sine beta, the tangential, plus g cos beta in the normal direction. I call this first equation for nt coordinate systems equation 1, and the second one equation 2. All I need to do is match like terms to figure out what v dot and rho are. So my tangential components, in the t direction, I've got v dot equal to minus g sine beta, which I've got as minus 5.34 meters per second squared. And then in the normal direction, v squared over rho is equal to g cos beta. So this is with v is equal to 12 meters per second, beta is 33 degrees, and g is 9.81 meters per second squared. Rearrange things. Our radius, 17.5 meters. So this problem is a little sneaky, and then it made you think about what we did a couple weeks ago, or a week ago. Projectile motion. I have to take an acceleration that I know, constant coming down, translate that into the coordinate system I care about, and relate that to the values we have. All right. All done. We'll see you guys next week.